topic we are going to discuss today is general principles and process of isolation of elements. Now, before starting the topic, let me ask you, why is that the principles and process of isolation of elements are important? This is because not only just metals and material science have a really important role to play in the engineering industry, but also they have a huge impact on the economy and lives of people in any country. So before we begin, we have to be familiar about certain terms. The first term here is minerals. As you already know, most of the elements occur in the Earth's crust in the combined state. There are very few elements like gold or platinum that occur in the native state. So these chemical compounds, in the form of which metal occur on the surface of the Earth, is called as a mineral. Now, it is not possible to extract a metal from every mineral. The mineral from which an ore can be extracted profitably, that is called as an ore. For example, iron is found in the form of carbonates, is found in the form of oxides, is found in the form of sulfides, but generally we prefer to extract iron from the oxide. Now, these are some of the important ores of metals. Aluminium is generally extracted from the bauxite ore. Iron, as I said, is generally extracted from the oxide ore. Copper and zinc can be extracted from any of these ores. Now, metallurgy actually consists of three main steps. There is a process of extraction and isolation of metal from any ore. It involves three major steps. The first step is called concentration of the ore. The second step is isolation of the metal from its concentrated ore. The final step is purification or refining. That is, whenever a metal is present on the Earth's crust in the form of its ore, it will be associated with some impurities, earthly impurities, which we call as the gangue. So, removal of gangue from the ore is the primary step involved in the extraction of any ore. This process is what we call as concentration. Now, concentration can be done using any of these methods like hydraulic washing, magnetic separation, growth flotation, or leaching. The kind of method adopted for concentration depends upon the property of the ore and the gangue. Like for example, if we are choosing hydraulic washing, it is generally done for ores that are generally heavier than the gangue. In this process, we allow the powdered ore to be washed by a stream of water. The lighter gangue particles are generally carried away with the water, and the heavier particles stay in the grooves so that they can be easily separated. The next method of separation is called magnetic separation. Magnetic separation is used when either the ore or the gangue particle has some magnetic properties. In magnetic separation, the powdered ore is allowed to move on a conveyor belt that are fitted with two rollers. The roller again have an electromagnet so that the particle that has magnetic property falls near to the roller, and the particle that does not have a magnetic property is carried away. So in this way, the separation of a magnetic substance and the non-magnetic substance is possible. Now, the next method is called growth flotation. Flotation is generally used for sulfide ores. It's based on the principle that the ore is generally wetted by the oily part, where the gangue particles are wetted by water. So here what we do is, you take the powdered ore and it is mixed with water. You also add some substances called conductors. Conductors are substances like pine oil, and you add froth stabilizers. The whole mixture is then agitated with the help of a paddle. So what happens, the ore which is more wetted by the oil gets collected along with the froth that is formed at the top. The gangue particles being wetted by the water gets collected at the down. Later the froth is taken away and the ore particles are separated. The next method of concentration is what we call as leaching. Leaching is usually applied when an ore is soluble in some particular solvent. For example, for the bauxite ore, you treat it with sodium hydroxide so that the Al2O3 is leached out as aluminium. Later on, this aluminate solution is utilized with carbon dioxide so that hydrated Al2O3 is obtained. This is later taken out and dried. Now once the process of concentration is done, the next process involves extraction of metal from the concentrate. For this we have to convert it into the oxide form. If the ores are of carbonates or hydrates, the method used for conversion of oxide is called as calcination. In calcination, you heat the ore at a high temperature in the absence of oxygen so that it is converted into the oxide. In the process, gases like carbon dioxide and water gets expelled. If the ores are of sulfides, generally the method adopted is called roasting. Roasting is done in the sufficient supply of air so that the gases like SO2 gets expelled. If the ore is of zinc sulfide, you treat it with oxygen, you get zinc oxide and sulfur dioxide gases expelled. These are the differences between calcination and roasting. Calcination is a process of heating in the absence of air. Roasting is the process of heating in the presence of air. In calcination, usually is done for carbonates ore. Roasting is generally done for sulfide ore. Again, the process of calcination expels gases like carbon dioxide, and the process of roasting expels gases like sulfur dioxide. Once the metal is converted into the oxide form, the next process involves reduction of the metal. Reduction means you keep the ore in the presence of a reducing agent. Now, what reducing agent is to be used depends upon the activities. Like for example, if the metal is very reactive, like potassium or sodium, the alkali metals or alkaline earth metals, generally you go for electrolysis as a method of reduction. If the metal is less reactive, like that of iron or zinc, you can use reducing agents like carbon or carbon monoxide. The temperature which we use for carrying out the reduction and the type of reducing agent to be used actually depends upon certain thermodynamical concepts. Now from thermodynamics, we know that delta G is equal to minus RT ln K. We also know that for any reaction to be feasible, the delta G value has to be negative. So when the delta G value happens to be negative, naturally the K value happens to be positive, or the reaction proceeds in the forward. Again, we know that delta G is equal to delta H minus T delta S. That is, for any reaction where the entropy change delta S will be positive. When we carry the reaction at a higher temperature, what happens? The T delta S happens to be more and more negative, so that the delta G value gets to be negative. It is also possible to change a non-spontaneous process into a spontaneous process by coupling it with another reaction. Like for suppose a reaction A to B has a delta G positive value. Now this can be coupled with another reaction C to D which has a very high negative value of delta G, so that the resultant becomes negative. Now it's always not necessary to do such delta G calculations to understand whether a process is feasible or not. We can also use the Ellingham diagram. Now Ellingham diagrams are plot of delta G of formation of oxides against temperature. Methods for which free energy of formation of the oxides is more negative can reduce those metals for which free energy of formation is less negative. That is, at a temperature, any element will reduce the oxide of other metal which lie above it in the Ellingham diagram. Here you can see at above 1623 degrees Celsius, aluminium has the capability to reduce magnesium oxide, and below that temperature, magnesium reduces aluminium oxide. So in such way, you can choose an appropriate reducing agent and a temperature to undergo reduction of any oxide of. Now we will see the process of extraction of iron from its oxide ore. That is the process of reduction. Now iron, as I have already said, is extracted from its oxide. The oxides are subject to concentration followed by calcination, and this calcite ore is reduced in a blast furnace. For this purpose, this is a blast furnace. Blast furnace is a cylindrical kind of furnace which is narrow toward the top and the bottom. And into the glass furnace, we feed the oxide of iron along with coke and limestone. The purpose of adding limestone is it serves as a flux. That is, the flux removes the gas particles so as to form the slag. The coke added is used for the reduction and it also acts as a fuel. Now, different kinds of reaction happens in the glass furnace. The reduction of the oxide form FeO actually takes place at a higher temperature down the glass furnace, and reduction of Fe2O3 and Fe3O4 happens at a lower temperature above the glass furnace. This is according to the Ellingham diagram. Here you can see that at a temperature below 1073 Kelvin, the CO2 line lies below the FeFeO line. Therefore, CO reduces the oxide of iron at that temperature, whereas above the 1773 Kelvin, you can find that the CCO line is much below the FeFeO line. So, carbon or coke is used for the reduction of Fe. Hence, here in the blast furnace at a higher temperature, that is towards the down of the blast furnace, you can see that the reaction taking place is carbon reacting with oxygen to give carbon dioxide. Along with that, the carbon dioxide further reacts with carbon so that you get carbon monoxide. A third reaction happening is FeO reacting with coke or carbon to give Fe and carbon monoxide. So, the reduction of FeO using coke happens towards the lower part of the blast furnace, whereas towards the higher part of the blast furnace, that is at a lower temperature, you see that Fe2O3 and Fe3O4 is reduced by carbon monoxide. Here Fe2O3 reacts with carbon monoxide to give you Fe3O4 and CO2, and Fe3O4 plus CO again gives you FeO and CO. Copper is usually extracted from the side. Right? To begin with, the ore is concentrated using purification, followed by the process of roasting. Then you heat it in the substance of dry oxygen, then you get the oxide form along the expulsion of sulfur dioxide. This oxide form is further reduced by heating it in the presence of coke. The coke can be used as a good reducing agent for the reduction of oxide, so that you get metallic copper deposited along with carbon monoxide. Now, coke is not only useful for the reduction of copper oxide, it can also be used in the purpose of extraction of zinc from the oxide form of it. As shown here, zinc oxide also, when you treat it with copper, you get metallic zinc along with carbon. The final method of process of extraction of metal is refining. Refining can be done in a number of methods. The type of method adopted generally depends upon the nature of the metal and the nature of the ingredient. Like for suppose the metal has a very low boiling point, like that of zinc or mercury, we can adopt the process called distillation. In distillation, the impure metal is heated in an iron retort, and the vapors that are involving are later condensed and collected in another vessel. Now, this is again based on the difference in boiling point of the impurity and the metal. Another method that can be adopted is called liquation. Now, liquation is generally adopted when the metal has a low melting point when compared to the impurity. The crude metal here is taken in a sloping earth. It is kept on top of a sloping earth and it is heated so that the metal that has a low melting point starts melting and it gradually flows down, whereas the impurity is held up the sloping earth. Again, another method of refining of metal is electrolytic refining. In electrolytic refining, generally you take the impure rod as an anode and you take a pure rod as a cathode. This method is generally adopted for purification of metals like copper or silver or gold. Like for suppose we are purifying copper. In this case, you take impure copper as the anode and you take pure copper as the cathode. And the electrolyte That is, suppose if copper is taken, we can take the electrolyte as a copper sulfate. Now, when electricity is passed, what happens is copper from the anode moved into the solution as Cu2 plus ion, along with the release of 2 electrons. At the same time, copper from the solution get deposited onto the cathode as metallic copper. So in this way, as the process continues, you can see that the anode becomes thinner and thinner and the cathode becomes thicker and thicker. These are the two equations corresponding to it. There is Cu giving Cu2 plus 2 electrons to the anode, and the cathode Cu2 plus accept 2 electrons to get deposited as metallic. Yet another method of refining is called zone refining. Zone refining is generally done to get extra pure metals like that of germanium or silicon. In zone refining, we generally take a impure metal in the form of a rod, and a circular heater is passed over the rod. So this is based on the principle that the impurities are generally soluble in the melt, and when the process of heating goes on, the pure metal gets crystallized on one side and the impurities are carried along with the. This is repeated over and over again, so that at the end you get the impurities towards the end of the rod, which can be later discarded or cut off. In some cases, for the process of refining, you also use the thermal decomposition method. In a thermal decomposition method, the metal is converted into a volatile form or a volatile compound, which later decomposes to give back the pure. So, the basic requirement to carry out thermal decomposition method is that first the metal has to get converted into a volatile compound on reacting with some chemical substance. The second condition is that this volatile compound should be capable of decomposing at a higher temperature. Now here we have two processes. One is called Mond's process and the other is called Van Arkel process. In Mond's process, actually we treat nickel with carbon monoxide so as to get the complex nickel tetracarbonyl. This nickel tetracarbonyl at a higher temperature of about 450 to 470 Kelvin, it decomposes to give back the pure nickel and the carbon. Now, in Van Arkel process is usually obtained is generally used for preparing pure zirconium metal. In Van Arkel process, you treat zirconium with iodine so that it forms zirconium tetraiodide. Zirconium tetraiodide again at a high temperature of about 1800 Kelvin, it decomposes to give back zirconium and iodine. So in this way, the pure metal is again. The fifth method of refining is called chromatography. Chromatography is based on the principle that different substances are adsorbed on the surface of an adsorbent in different levels. That is, usually the process of chromatography consists of a mobile phase and a stationary phase. Stationary phases are usually solids and mobile phases are usually gases or liquids. Now, depending upon the physical state of these phases, you have different kinds of chromatography like partition chromatography, column chromatography, gas chromatography, etc. Now, in this process, usually you dissolve the mixture in a mobile phase, and this mobile phase, when it is carried over the stationary phase, depending upon the nature of the chemical substance, they are absorbed to different extents. After the absorption, they are removed or diluted from the surface of the adsorbent. So, these are the ways of refining of metal.
Thus, as seen here, a metal is extracted from its ore through a number of methods. Now, these methods can be summarized as given below. The first step involves concentration of the ore. The method adopted for the concentration of any ore generally depends upon the property of the ore or the metal and the gangue impurities. Here mainly we have discussed four methods. One is hydraulic washing, the second is called magnetic separation, third is called fourth flotation, and the fourth one is called leaching. Once the ore has been concentrated, the next method is conversion of the concentrated ore into the oxide form. For this, generally we can go for the method of calcination or we choose the method of roasting. Now, once the ore is converted into the oxide form, the next method is called reduction. Now, for reduction, the kind of reducing agent selected generally depends upon the reactivity of the metal. We can also use thermodynamic concepts and the Ellingham to decide at which temperature and what reducing agent is to be used. The final and the last method of involved in the process of extraction is called refining. Here again, we have discussed a few methods. The first one was distillation. Then you have liquation. You have electrolytic refining. We have also discussed zone refining, vapor phase refining, and finally chromatographic method of separation.